So welcome everyone. We just resumed the session for this afternoon, and there is a little change in the schedule. So actually, Carolina is not going to present, but we have Rafael Bernar that is going to take her slot, and he's going to talk about failing charges into a Schwarzschild black hole, a quantum approach to radiation emission. So you're
So thank you for the nice introduction. So as we were saying, so was supposed to give the talk on Thursday, I think, but Carolina had some problems, and so we are switching the presentation. So I'm presenting today. So I'm probably say sorry in advance if I'm saying some stuff that looks improvised. It's because it is improvised. So the talk is about falling charges in a Schwarzschild black hole, a quantum approach to radiation emission. So it was a work done in collaboration with João, that's here in the audience, Atsushi Higuchi from University of York, and Luis Crispino from here as well. And this is a really simple setting. Basically, what we want to do is basically you want to throw a charge into a black hole, and you want to compute the radiation emission from this in this scenario, right? So, and you have an electromagnetic charge, and of course it's coupled with the electromagnetic field, and you want to compute the radiation from that. And it's a work that is actually, it's a very old problem, but you can try to study that with, for instance, green functions, or you can do what we did here, which basically you try to study that using a quantum framework. So use quantum field theory in curved space-times to try to study that. And of course you can study that with you have some things to work out in this setting. So for instance, of course you have to study the electromagnetic field in a curved background of a black hole. So you have to know how to quantize it. And you also have to model how the particle will fall into the black hole. So you have some parameters like the initial velocity in which you throw the particle, and the initial position from which the particle starts falling into the black hole. And we will see that there are some connections with black hole quasi-normal modes in this case, and we will also try to study the zero frequency limit from that. And also, if there is time, we will try to discuss how the point particle model in this case fails in some sense, and what you can do to try to circumvent that. So let's start with the electromagnetic field. I'll try to go quickly about that, but so the way that we do that is you start with the Lagrangian for the Maxwell field, and with this Lagrangian you have the Euler-Lagrange equation, so the equations of motions, right? And you can have some mode solutions. So this is important in order to quantize it, because you have some mode solutions that will have this form here, and which we call positive frequency solutions, because the time-dependent part is e to the minus I omega t, and omega is positive. And with those solutions, if you work out the equations of motions, you see that you have also some quantum numbers that you have to take into account. Basically, the angular dependence will have some, you need some quantum numbers for that, so L and M. And also, because the space-time has two infinities, right? So you have the the asymptotic infinity, and you have the horizon. So you have two boundaries for a space-time. So you have two independent modes of two solutions, two independently coupled solutions. So you have one that's what we call the in modes. So the in modes, they are purely incoming from the past, no infinity. So I don't have a pointer here, but it's the modes that are represented in the left part there of the figure. But you also have what we call the up modes. So the up modes are the ones that are purely incoming from the past horizon or from the white hole horizon. And with those modes in mind, you have these mode solutions. Because you are working with a gauge field, you also have 4 polarization modes. Huh? But of course you have 4 of them, 2 of them are physical. One, it's what we call pure gauge, and the other one is what we call non-physical because they have negative norm. And of course, the way to fix that in our setting is you impose a gauge condition on the space of states, and this is represented by this operator equation here. So the gauge operator working in the physical space of states is 0, right? And so with that, you only get 2 physical modes, as I said. One of them, so these are the 2 physical modes. So, but the one that is selected there is, if we look at how the mode is, the form of the mode there, we can see that it's the only one that has a radial component of the vector field. And this is important because in the problem that we are going to try to analyze, as the particle falls into the black hole, it will only excite the mode that is the one mode, the first mode, because it's the only one that has a radial part that's different from 0. So in a sense, we have 2 physical modes, but we only need to worry about one of those. And of course, this quantization, this separation of modes like that is actually, it's done in previous works, including, of course, Crispino. And so the thing is, you want to study an infalling charge into the black hole. So the way we do that is you pick a source term. So the current is like in the equation there, and so the current will depend on the velocity, the 4 velocity of the charge, which is written like that. So you basically you want a geodesic falling, a particle falling in a geodesic trajectory into the black hole. So it's like that. So I'll quickly go from that. So we have some interesting things here because you can select the point in which you will drop your charge and how you drop it. So if you throw the charge into the black hole or not, so you have 2 parameters for that, which is basically the initial position, R0, and the initial velocity, which is V0, right? And you can see that you have some, in a sense, you have a way in which the velocity of the charge depends on how you throw it into the black hole, and you get some plots like that. So the plot is the velocity of the charge as a position as a function of the position r when you vary the initial velocity of the charge, right? So for instance, you can see that for a certain value of the initial velocity, you only have deceleration as the particle falls into the black hole, and for certain values, for smaller values than a certain fixed value, you have acceleration and deceleration. Yeah. Okay, so how you can analyze the radiation? So you can analyze the radiation by you quantize the field, and then you can try to compute some observable. In this case, you compute the one particle emission amplitude, which is given by that. So, sorry. Yeah, so the one particle emission amplitude is that sandwich with the state with no particles and the state with one particle. And with this, you get some, you have to solve an integral, right? And with the current, you solve this integral, and now you have the one particle emission amplitude. You square it, then you get the probability of emission of radiation. Right? So it's a very simple thing. So of course in this setting it's a bit harder to do that, but it's something that easily a master's students, maybe a finishing undergraduate, can do as a simple exercise to do that, for instance, for the scalar field, right? And so the energy spectrum, you can compute it with those. So remember, this A quantity is the probability, the transition amplitude. You square it, you get the probability probability value of emission, right? So you can compute the total energy as a function of the frequency, right? So the energy spectrum, and you can also compute the total emitted energy, and so, right? Right, so you can also, of course, you can try to do that numerically. So what you need now is you need the function, the radial function of the field, that you can solve it numerically. But of course you can also try to study this in the zero frequency limit. So you make an approximation that omega is near zero, and of course this is very simple, because in this case the function will be just something times a spherical Bessel function, and the energy emitted in the zero frequency limit will be this expression here that's not really that good, but at least you can work with that, right? So it will depend on some special functions, right? And of course you can try to compare that. For instance, you can see that the zero frequency limits are the numbers on the left, and the numerical value which we consider the exact one are the right ones, right? So one thing is, of course, you can try to compute this energy spectrum, right? And you get something like that, which is very interesting because you can see some dependency, some you can separate the spectrum in the quantum numbers that of emission, right? So you can analyze it multiple by multiple, and you have something like that. So those results are for the usual case. So the usual case is you drop the charge from infinity, and you drop it with initial velocity equals 0, right? So you just you drop it at infinity, and that's it, and you let it fall into the black hole, and you get something like that. Uh, so this is the plot, right? And of course, we can see something that is expected is that not a lot of the energy is emitted to the infinity as you drop the charge, right? So you can see that's basically the total energy that's emitted in electromagnetic radiation is 0.17% of the total energy of the particle. So one interesting thing is that as you increase the initial velocity, you can see that the way in which the spectrum, so maybe it's my computer, so don't worry about it. Yeah, so maybe it's my voice. No? Vocês podem ver, alguém pode ver o que é? Não sei se é. Não, mas não tem nem internet aqui. Tá desconectado meu computador. Okay, so let's try to. Yeah, maybe it's Discord, but don't worry about it. So one interesting thing is, as you increase the initial velocity, you can see that the spectrum for each multipole, it drops down dramatically at some values, and those values are actually the quasi-normal frequencies of the field. So in a sense, you can get a signature from the field. You get a signature from the space-time plus field from those results here. And of course, you also find that on other values of the velocity, but it's a striking feature of this when you increase the initial velocity. Right, and of course you can obviously increase the total energy emitted as you increase the initial velocity. So you can use the zero frequency limit, which will basically be a good approximation for the shaded area in the graph. So with the estimation of with the zero frequency limit, and of course you can do something that's basically in the zero frequency limit. You can basically approximate the energy spectrum by a constant value, and the total energy will be just this constant value times a certain frequency, and in this case the certain frequency in which you can use is the quasi-normal frequency, the first quasi-normal frequency from the field in this setting. And it's an approximation that works very well because it's basically less than 3%. The error is less than 3%. So, and we can you can actually approximate it by that. So using that expression, you can use an approximation like that for V naught equals 1, right? So V naught equals 1 is basically when you try to throw the initial particle with the velocity equals to the speed of light, right? So it's not really realistic, but it's something in which you can look at. Right, so let's so the other thing in which you can look at is when you try to throw the particle into the black hole, but instead of dropping the charge from infinity, you drop the charge near the black hole. So they are not In this case, there are nodes in which you are dropping the charge is basically near the light ring, right? And you get something like that, which is way different. So you have some shifts in the quasi-normal frequency things, but I don't think I'll talk about that. But so the interesting thing is, let me see if I... Right, so the interesting thing is as you drop the charge nearer, as you drop the charge closer to the black hole, you increase the dependency of the spectrum from the lower multiples. So you can see that in this case, for instance, more than half of the total energy comes from the dipole radiation. Right, so one thing that I did not tell you about is, because you can look at the radiation to the infinity, so the emitted radiation to infinity, but you can also look at the radiation absorbed into the black hole. And in this case, it's very easy to analyze that, because when you are looking to the radiation to infinity, you only have to look at the in modes. But if you look at the up modes, so the other independent modes, you get information from the absorbed radiation. And in this case, it's interesting to look at, but if you try to compute the total energy, you get something which is divergent. And this is something that's a bit puzzling, right? But the thing is that one thing in which you can think about this divergence is because as you throw the charge into the black hole, of course, at some point, the charge will fall into the black hole. And as the charge falls into the black hole, you have an absorbed radiation that is actually the energy from the charge. So, but not really the energy from the charge, the energy from the Coulomb field that the charge carries into the black hole. And as we know, the Coulomb field from the charge is something which is basically dependent 1 over r squared, right? And this is, we know that this is actually an infinite amount of energy in a point charge model, right? So one thing that you can do is basically, instead of throwing a point charge into the black hole, you throw an extended string into the black hole. So you give it a small extension in some direction, in this case the radial direction, and so you can model that using our setting, and you can actually, you do not cancel the divergence, but you tame it a little bit, so the divergence gets better. And we expect that if you, instead of throwing just an extended string, you throw a thing which has volume, in a sense, you won't have anything of those divergences, because of course now the Coulomb field is a thing that is well behaved in a sense. And so I think I had an animation here, but it's not working. Yeah. So maybe. Yeah. Yeah. So what the animation was supposed to show is, as you increase the size of the string, so this parameter delta t is basically the size of the string, because it's the time in which you can basically traverse from one end of the string to the other. So as you increase the time, you basically you tame the behavior of the divergence, but of course the animation is not working. So some conclusions from that is, of course, you can analyze radiation settings around black holes using quantum field theory in curved space. In this case, the radiation spectrum presents some signatures from the black hole quasi-normal modes. One thing that I did not say is the emitted radiation to infinity is divergent when the initial velocity is the speed of light. But of course, I don't think we have to worry too much about that, because you don't expect to throw a charge with the initial velocity being the speed of light, right? But the other thing is that the radiation going into the black hole is divergent, but we know that this is basically from the Coulombic field that's carried by the charge into the black hole, and this has infinite energy. And you can try to test that in some sense by throwing an extended object into the black hole. And we expect that if you try to throw a bigger thing into the black hole, so a thing which has volume, you won't have any of those divergences. And some perspectives, basically, we can try to ride in spiral, right? So of course, you can try to throw a particle into a black hole, but instead of throwing radially, you let it go round to the black hole, and of course you can analyze this case in this setting, right? So I think that's it, and thank you for attention.
Thank you, Rafael, for the nice talk. I think we have a couple of minutes for questions. Any questions? If not, I have a question myself. So essentially what you are doing is you are dropping a particle, but the velocity is radial velocity, right? Or what happens if you just you drop the particles, but you give some angular momentum? Is gonna change, or?
Yeah, so this one. Yeah, so if you try to throw it with non-zero angular momentum, it's basically riding this in spiral in this sense, right? So you, and of course, I think we have some results from that, but not in the electromagnetic case, and of course, as you try to throw it into the black hole, so you basically increase the time in which the particle spins around the black hole, and of course, you can increase the radiation emitted to infinity as at least as a fraction of the total energy, but you have to compute.
You mentioned that the maximum energy that can be radiated is around 70% equal to 1.
Yeah.
Now I'm wondering if you drop the particle with some angular momentum, you are going to increase it to, I don't know, 50% or 50%.
Yeah. You expect that to happen, but of course you have to compute it. So, and this is something that João Paulo should do, I think, because he's actually I'm presenting the work, but the main I should have said that in the beginning, but the main workforce of this work is João Paulo, that's there in the audience.
All right, more questions? If not, then thanks, Rafael, once again.